Good afternoon. This is the lecture on Chapter 4 of our textbook. The subject is closed system energy analysis, and this vodcast is for the lectures that would normally be in class, dated March 4th and March 5th. So this lecture might go a little long. I'm not really sure. I'll let you know at the end how long it is, and I'll put it up on Moodle. But it may be a little bit over an hour, but in any case, it will be the substitute for 2 lecture days in class. There will be an assignment at the end of the lecture, and I'll also post that to Moodle. And then if you have any questions about this material and the homework that you've done, bring them into class on Tuesday, March 10th, and we'll take care of any questions or problems that you have. The first thing I'd like to do before I get started with the new material, which is about the energy balance, in class today, March 3rd, we talked about boundary work. And there was a problem that I ran across that I wanted to do in terms of boundary work. It's problem 4.9 in your textbook. And it really exemplifies another aspect of boundary work that we didn't talk about, or another method that you could use to calculate boundary work. So I wanted to go through this process with you. Problem 4.9 reads, we have a cubic meter of saturated liquid water at 200 degrees centigrade, and it's expanded isothermally in a closed system until its quality is 80%. Determine the total work produced by this expansion in kilojoules. Okay, now here's the important thing. If we look at this expansion, we know that boundary work is can be calculated using the equation PdV. Okay, the problem with this is that if we have it says it's isobaric. Does it say that? Yeah, we have something that looks like this. P times the integral of dV, which is just P times V2 minus V1. And the reason that this is true is because we are told it's an isobaric process. Now, the problem becomes we're told that we have a cubic meter. It's at 200 degrees centigrade, and it's a saturated liquid. Well, what does that mean? That means that we're right here on the two-phase diagram. And it is expanded isothermally. It says constant pressure. That's why we could use this equation till we get to an 80% quality steam. This is not a gas. Okay, we've gone over this like many, many times, but I want to reiterate, this is not a gas. So can we use any of our equations of state? Can we use the ideal gas law? Can we use PV is equal to Z nRUT? The answer is no, because we're dealing with something that is primarily a liquid, or the part of it that's in the gas phase is not sufficient enough to approximate it as an ideal gas. Well, what's the good news? Because it's water, and because we have the conditions, we can use our property tables or steam tables. All right, now we're told in the problem that we have 1 cubic meter, and we are at 200 degrees centigrade. And we're told that it's saturated water. Well, for saturated water, when we're saturated, pressure and temperature are not independent, are they? So if we find saturated water at 200 degrees centigrade out of our steam tables, we are going to be able to determine that pressure that is the saturation pressure at 200 degrees. That pressure will be consistent throughout. Then we can find, we'll have V1 right here. We can find V2 using the relationship. Well, we talked about intensive properties. Little v is equal to x times v sub g plus 1 minus x times v sub f. If you think about it, the mass is the same throughout, so we could multiply each term by mass and we could just talk about extensive properties as well. So we could say the volume at time 2 is equal to x times, well, I guess I can't really do that. Let's do it like this. X, I'm going to factor out an m, I think is going to be the easiest way to just write this. M times x times v sub g plus 1 minus x times v sub f. So that will give us our volume at time 2. There's an easier way I could have set this up, but here we go anyway. All right, so let's go to the property tables. All right, here we are. First of all, we have to remember we're working in the metric system, and we're talking about the substance of water. So it will be in Appendix 1, and we need to come back to our saturated liquid or saturated water table. We can base it on temperature. It doesn't matter because since it's in the saturated region, temperature and pressure are going to be the same. But what I see here is that at a temperature which was given of 200 degrees, my saturation pressure is 1554.9. The saturated pressure, I'm going to write this on the board, which we'll see in just a minute, is 1554.9 in units of kPa. So when I do my work, my boundary work calculation, I will need that. I do not actually have a mass, but we're going to think about this. Well, I guess I have to think about that for a minute as well. Anyway, my V sub G and my V sub F values, let me write them down for the saturated liquid because then I can back the mass out. So when I have saturated liquid, my V at state 1, little v, I'm writing this on the board. Maybe I should write it in the margin over here so you can see what I'm talking about. Okay, I've just realized that I do not have the mass. So what I need to realize is that at time 1, my little V sub 1, or my specific volume, is going to be V sub F at those conditions of saturation. Since I know my volume as being 1 cubic meter, I also know that little v is equal to big V divided by mass. So I can back out the mass by saying mass is equal to big V divided by little v. Okay, so that's the calculation I'm going to do. So I need to pick up my V sub F value at those conditions, which is right, here's my condition, 200, 1544. My V sub F is this value, 0.001157. And I will also need to find the 80% of the second state, my V sub G, which is 0.12721. All right, so I'm going to switch back to the board after I write those values down on the board. Little v1 is 0.001157 cubic meters per kilogram. And that is V sub F at those conditions. I'll also need V sub G at those conditions, which, because we're talking about vapor, is quite a bit higher. It's actually 2 orders of magnitude, so 100 times, actually 1,000 times larger. So V sub G is 0.12721, also in units of cubic meter per kilogram. Sorry, it's just 100 times, I said 1,000. Okay, so I'm going to switch back to the board so you can see what we're talking about. All right, so I've written the values down here. So in order to find, I know V1, cubic meter, I know P1 from my tables, which is 1554.9 kPa. Now I need to find V sub 2, and I'm going to use this formula to do it. So I'll first need mass. So I can use V sub 1, little v sub 1, and big V sub 1 in order to find mass. And since it's a closed system, that's not going to change, is it? So, as I had said before, mass is equal to extensive volume divided by specific volume So in this case, it's 1 cubic meter divided by 0.001157, which is the value out of the tables, cubic meters per kilogram. Meters cubed cancel, kilograms snaps up to the top, and I get a mass of the reciprocal of 0.001157, which is, oops, boy, that is a lot of water. 864.3 kilograms. But it's correct. We have a full cubic meter of liquid at the initial case, at the initial state. And we know that the density of a cubic meter of water can be as much as 1,000. So that's actually, it's okay. All right, so now what we need to do is to find our V sub 2, which is going to be our mass, 864.3, times our x value, which we are told is 0.8, times our V sub g value, which is 0.12721, plus 1 minus x, which is 0.2, times V sub f, 0.001157, and these values are in cubic meters per kilogram. This is in kilogram, so this entire value will be in cubic meters. I'm going to scoot the, there, so you can see that a little bit better. All right, I'm going to scoot the camera over. So now we're going to do this calculation. We get 0.8 times 0.12721, and we add to that 0.2 times 0.001157, and I multiply the whole thing by the mass of 864.3, and I get an answer that my volume at state 2 is 88.1 cubic meters. All right, so now here, this is 88.1 cubic meters. And we know that that was cubic meters. So then I multiply that by the pressure, which is constant, 1554.9 kPa. If you remember, a kPa, a kilopascal, is a Newton, 1,000 Newton, kilonewton per meter squared. So what we get for units here will be kilonewton meter or kilojoules. So I take that value of 88.1, subtract the initial volume of 1, multiply it by the pressure 1554.9, and my value of work in kilojoules is 135,522.1, or I could write that as 135.5 megajoules. So there you go. That's a lot of work, but that's the answer. So I wanted to show you that problem. I think this is an important demonstration of another way that we can get to data if we don't have any particular good data. So the next problem I'm going to work then is one in the closed system energy analysis category, and it's problem 4-29. Now I want you to use this as a model for problems that you might work, that you will work for your homework. But basically, every time you do a problem like this, you need to do the setup. You need to start with the base equation, and you need to think whether energy is going in or out. Q minus W equals delta E of the system. Okay, so I've written that equation up here on the board, and now we'll work with this to finish this problem. I'll be all right. I won't scoot that over here. The Q is on the edge of the film, but you can still see it. All right, so for problem 4-29, says we have half a meter cubed, and it's a rigid tank, contains refrigerant R134A initially at 160 kPa and 40% quality. Heat is transferred to the refrigerant until the pressure reaches 700 kPa. Determine the mass of the refrigerant, the amount of the heat transferred, and also show this on a PV diagram with respect to saturation lines. All right, let's go back to this problem. There's no particular change in potential energy, is there? We're not raising it or letting it go over a waterfall or anything like that. There's also no particular change in kinetic energy because it's not speeding up or slowing down. What about work? Remember, work is the integral of PdV. We're told this is a rigid tank. That means that the volume does not change. So dV is equal to 0. And if dV is equal to 0, the integral of PdV is also equal to 0. And therefore, work in a rigid tank is equal to 0. That means that for us, Q, in or out, is equal to delta U. Okay, so this becomes a problem of using the property tables to get this data, and also it asks us to draw it on a diagram. It asks us for a PV diagram. So P over here, V down here. All right, how do we find delta U? Well, it's delta capital U, so that's mass times U of state 2 minus U of state 1. These are properties. If we can fix our states, we can fix the U values. So what are we told? We have a 0.5 cubic meter rigid tank. So my volume in time 1 is equal to my volume at time 2 is equal to 0.5 cubic meters. The substance is R134A. So we know which tables to use. And it's initially at 160 kPa, 40% quality. 160 kPa is P1, X1 is 40%. All right, now it says that we heat transfer until it reaches 700 kPa. P2 is 700 kPa. Q goes in. Something's going to change. It's not going to be the same steam quality. It's still going to be R134A. The volume is still going to be the same. Is the mass still going to be the same? Absolutely. It's a closed system. So the mass at time 1 and the mass at time 2 are the same. Now, this is not really obvious, but if the volume and the mass here are the same as the volume and the mass here, the specific volume here has to be equal to the specific volume here, because specific volume is volume divided by mass, or the other way around. So they have to be the same. Now, you're always, and I'm sorry, the other way around is density, but mass divided by volume is density, volume divided by mass is specific volume. But you have the same specific volume. It's not necessarily going to be in the same state. This is a two-phase fluid. We don't know what this is. However, we do know the pressure, and after we calculate specific volume over here, we can use that over here, and specific volume and pressure are two independent properties, so we can fix the state over here and make a determination about something. Not really sure what at this point. About what Q is, what our U is. We can find U2 based on pressure at state 2, specific volume at state 2. First order of business, we're going to find specific volume at state 1. Specific volume at state 1, using our general formula for X, for two-phase fluids, X times V sub G plus 1 minus X times V sub F. Our X is 40%, so this is 0.4. That means 1 minus X is 0.6. We go to the tables to find V sub G and V sub F for our fluid, which in this case is refrigerant. So we go past the water tables, down to the refrigerant tables. There we go. And we look for the initial conditions. 160 kPa, 40% quality steam. That means that we need to use pressure-based tables. There it is. And we can see what our saturation temperature is going to be. We can also see our V sub F value and our V sub G value. So at that pressure, our V sub F value is this, and our V sub G value is this. Okay, so V sub G is 0.12348, 0.12348, and our V sub F value is 0.0007437. I'm going to flip back over to the board now. I'll show you where I've written that right here. Okay, so now we can calculate our specific volume at state 1. So 0.4 times 0.1238, and we add that to 0.6 times 0.0007437, and that value altogether is 0.0498 cubic meters per kilogram. Okay, as we've talked about then, this value has to be the same as little v sub 2, 0.0498 cubic meters per kilogram. So now I have an unfixed state. I do not know what this state is. Oh, before I leave, I better pick up my u at state 1 too also, right? Because that's what I need in my equation. So if I come over here to the property tables again, at 160, 40% quality, this is my U sub F, this is my U sub G. So I'll do that calculation, same sort of a thing. U sub 1, I'm writing this on the board, and I will flip over here and show you my calculation in just a minute, is equal to X, which is 0.4, times the U sub G value, 221.35, plus 1 minus X, which is 0.6, times the U sub F value, 31.09. And I'm going to get that value in kilojoules per kilogram. Okay, now I'll switch back over. All right, so that calculation for you is right here. And if I run the numbers, I get 0.4 times 221.35. Add to that 0.6 times 31.09, and that entire value is 107.194, so I'll just call it 107.2 kilojoules per kilogram. I also need to find the mass. Mass is going to be the same here and here, so I can use specific volume at time 1 and the volume, which is consistent, to find the mass. So basically I can say specific volume at time 1 is equal to the volume at time 1, which is unchanged, divided by the mass at time 1, also unchanged. And I can back out the mass from that by saying the mass. I'm dropping my subscripts because they're all the same. And so I have 0.5 cubic meters volume, and my specific volume is 0.0498 cubic meters per kilogram. Cubic meters cancels out, kilograms flips up to the top. And my volume is, excuse me, my mass is 0.5 divided by 0.0498. My mass is 10 kilograms. Okay. And of course I know it's a closed system, it's going to be the same from there to there. All right, so now I know my little v2. I know this. I need to use these two properties, my pressure of 700 kPa and my specific volume of 0.0498 to fix the final state. Back to the steam tables. Okay, now if I go here, if I look at my saturated numbers, if I look at the pressure that is given to me for state 2, 700 kPa, if I come across here and I look at my values for V sub F and V sub G, I see that my value for V sub G is too small. In other words, if I were on the boundary of the curve, the two-phase curve, here would be my specific volume, V sub G, and my fluid is going to be over here. So what does that mean? That means it's superheated. So I need to page through the superheated tables and find 700 kPa, which is going to be 0.7 MPa. Okay, so it's right here in the top right-hand corner, pressure of 700 MPa. I can also see, for this, I may want to write this down as well, at 700 kPa, I'm looking at a specific volume of, let's see, I want to find something close to 0.0498, 0.04, all right, 0.048 is the largest value I can find. So I'm just going to approximate that as having a specific volume, excuse me, having a temperature of that last temperature, which is 160 degrees centigrade. And that gives me a U value. We go ahead and circle it here. 700, 160, U value of 367.29. 367.29 kilojoules per kilogram. Now the other thing I want to note here is that at 0.7 MPa, my temperatures, the saturation temperature, is going to be 27 degrees, 26.69, but 27 degrees centigrade. Okay, the reason I want to do that is when I draw my curve, I may want to think about where I am in terms of those boundaries. Okay, I also want to go back. I did not write down the temperature for my initial state. But at a pressure of 160 kPa, my saturation temperature is negative 15.6. Tsat is negative 15.6 degrees centigrade. All right. So I may have to make some assumptions about how this process is going to occur. But we'll take a look at that after we do our calculation. All right. Right now, it asks us to find Q. We know that Q is equal to delta U, which is equal to mass, times U2 minus U1. We found our mass to be 10 kilograms. We found our U2 value, which is over here. This is U2. I didn't write down the symbol. 367.29 in units of kilojoules per kilogram. We calculated our U1 value to be 107.2 kilojoules per kilogram. And you multiply kilojoules per kilogram times kilograms, cancel out. My overall unit comes out to be a kilojoule. And if I do the calculation, 367.29 minus 107.2 and multiply that number by 10, I get 2600 kilojoules, or we could write it as 2.6 megajoules. And that is the heat that goes in to the system in order to make that change occur. And it is a phase change, isn't it? We start out with a two-phase fluid, and we move into a superheated vapor. So when I read through the problem, it says the amount of heat transferred, and also show the process on a PV diagram with respect to saturation lines. Okay, so I need to come back over here and look at my PV diagram. Now, here's the deal. We're changing pressure. We are going from 160 to 700. We're going from two-phase to superheated, and we're going from a temperature, which really doesn't show on here, of -15 up to 27 degrees, which for a refrigerant, for our 134A, is actually quite high. Okay, so what that means is at state 1, if this pressure were 160 kPa, we start at 160 kPa in the two-phase region, 40% of the way through. All right? And we end up on the PV diagram. Once again, this value of little v is 0.0498, so that's almost 0.05 in units of cubic meters per kilogram in units of kPa. All right? And we end up over here at 700, quite a bit higher, and a specific volume of 0.0498. 0.04, oh, it's the same, of course it is. So that means that on the specific, this is going to come up here. You know what? This is really strange. That's actually going to put us up here, isn't it? Because we have the same specific volume and a much higher pressure. So, and that actually explains why it came off of the charts, because we're actually kind of supercritical. But that's basically what the line looks like. So we started at a pressure of 160.4. Oh, no, I don't think that's what it is. I'm kind of thinking it would go like this. It could go straight up like that, or it could have gone around the two-phase region, or we could have gone through the two-phase region. There's really no way at this point to tell what that relationship looks like, because we just know the beginning state and the end state. Interesting. The other thing I would probably like to look at before I determine if I like that very well or not, I mean the path, I know my endpoints, but if I look at the path, if I go back here and I see what is my critical pressure for refrigerant R134A, here's my table. There we go. Critical points for R134A, tetrafluorine, 4 MPa, and this would be 0.7 MPa. So this is actually going to be like this, where that means that this chart probably leans over. If this is up here, and this pressure is down here, and it's superheated, but my specific volume stays the same, what does the shape of this curve look like? That's really exaggerated, but it would be up higher because the critical pressure is quite a bit higher than the 700. So let me show that to you. Yeah, so we're going to have a situation like this where we're actually in the superheated range. Critical pressure is going to be up here, so the curve is going to be a little bit strange. Very interesting problem. All right. So that's taken a little over half hour. Let's do at least one more problem to get you rolling. This time we'll do a little bit of work. You've done a lot of work. You found a lot of work in the previous section, but I'm going to give you another problem to help you find work in this section. I'll rewrite that equation too, because we have different parameters that will be needed, or that will go to 0, or that we'll assume to be 0, or whatever. So let's take a look. Okay, so no matter what, we start with our first law, energy balance for a closed system. Okay, and since that last problem, 29, had a rigid tank, we had no work. So let's find a problem that has some work associated with it. Let's look at 427, or let's look at, no, I don't want another rigid tank. Okay, let's look at 432. There's lots of good information in this problem without getting overly complicated. So 432, we have a fixed mass of saturated water vapor. Saturated water vapor, X equals 1. A fixed mass of saturated water vapor at 400 kPa pressure is cooled isothermally until it's a saturated liquid, X equals 0. If it's cooled isothermally, what does that mean? That means the temperature at state 1 is equal to the temperature at state 2. Okay, it also means if you look at this, we're really talking about going from X equals 100% to X equals 0. So we're crossing the two-phase region. Temperature remains the same. Since pressure and temperature are not independent in the two-phase region, the pressure also remains the same. So that means the work for this process from 1 to 2 is equal to the integral of P dV, which since pressure is constant, is P times V2 minus V1. Right? Now, we don't really know what the mass of the water is. We may have to deal in intensive properties, in which case we could say the work per unit mass from 1 to 2 is equal to the pressure times specific volume at state 2 minus specific volume at state 1. We can also look at this problem. Let me take a look here. Calculating heat rejected. Okay. We could write each of these terms, once again, PE and KE go to 0, not moving, not falling. And we could divide each term by mass, because it's the same throughout. And then we could say little q, or the heat per unit mass, minus work per unit mass, is equal to delta U per unit mass, which are those intensive properties that we can get on the property tables. All right. So we need to calculate work per unit mass. We need to find these two values out of the table, and then we can calculate Q using the formula. So let's go ahead and go to the property tables for water. Oops, probably want to see those. So paging through, there's water. And we are told that the pressure is 400 kPa, so we definitely want to go to the pressure tables. There we go, 400 kPa right here. Let me erase some of this, and we'll underline the data for this problem. 400 kPa. Temperature 143.61. There are my V values. There are my U values, right? So on the board, I'm going to write temperature at both states is that saturation temperature of 143.61 degrees centigrade. Specific volume at state 1 is V sub G, isn't it? Because we're told that we're at 100% or saturated vapor. 0.46242 cubic meters per kilogram. And U at state 1 is also equal to U sub G. And that value is 2553.1 in units of kilojoules per kilogram. Okay, now over on the other side of the chart at my zeros, state 2, my V sub F is 0.001084, 0.001084, and U sub F, or U sub 2, is going to be 604.22. Same units. Okay, I'll flip you back over here to the camera. So I've written my values here after it's allowed to cool. My V value is 0.001084 cubic meters per kilogram. My U sub F, or my U value after it's allowed to cool, is 604.22. So I have my V values, I have my U values. First thing I can do, calculate work, isobaric work. So I have a pressure of 400 kPa, and my V sub 2 is 0.46242. My V sub, or that's my V sub 1, I'm sorry, got that backward. I'm thinking going from here to here. Let me read the problem again and make sure I'm going the correct way. Isothermally cooled. So my initial, this is my initial stuff, yeah. And this is my final stuff. So if I do V sub 2, it's this number, isn't it? 0.001084 minus V sub 1, which is 0.46242 cubic meters per kilogram. Okay. And I notice kPa, I know that kPa times cubic meter turns out to be a kilojoule, but I still have this because I haven't converted, I don't have the mass. So I have to use, I can just write my answer down in kilojoules per kilogram, or per mass unit. 0.001084 minus 0.46242, and I multiply that by 400 kPa. And I get a value of, for work, from 1 to 2, of negative 184.5. What does the negative mean? Work is done on the system. It's a compression. Okay, so we'd already talked about that. If it's compressed, that means that the work is a negative value. It goes into the equation as a negative. So we'll take a look at that in just a second. All right, now we have our work value. Do we have our delta U? Well, that's easy to find because delta U is just U2 minus U1. This is my second value, so 604.22 minus U1, 2553.1. Both of those are in units of kilojoules per kilogram. So if I do the subtraction, 604.22 minus 2553.1, I get a value of negative 1948.88 kilojoules per kilogram. All right, so now let's take those two values, plug them into our closed system energy balance, solve for Q. Q minus W minus negative 184.5, being very careful to show you the sign convention, equals negative 1948.88. This becomes plus, negative negative is a plus, so it comes over here as a negative. Q equals negative 1948.88 minus 184.5. So my Q value is negative 2133.38 kilojoules per kilogram. Q is negative. What does that mean? Q went out of the system. Heat went out of the system. Is that consistent with something going from 100% steam quality to 0% steam quality? Absolutely. The final state of the system is lower. The final energy state of the system is lower, so heat had to be removed. So we did some work by this compression, by the boundary work, on the system, and then heat went out, so that the final stage, or the final state of the system, is at a lower energy state than the initial system. All right, ladies and gentlemen, well, that's it for March 4th and March 5th. I will put some homework problems up on Moodle for you to do, and we'll talk about them on Tuesday, March 10th. Thanks. Talk to you later.